I'll be talking about back to string theory. I'll be talking about discrete symmetries of Calabi-Yau manifolds. First, I can point out that today is a very special day because back in 2012, on this very date, the Higgs boson was announced. However, contrary to popular belief, the real discoverer is actually the physics spam filter at Oxford. Look at this subject that the Higgs boson does not exist when to spam directly. Anyway, broadly speaking, I work on string phenomenology, and the holy grail of our field is to embed the standard model of particle physics within the framework of string. Now, that involves several different things. One, of course, has to reproduce the particle content, the quantum constants, correctly grade the masses of the particles, as well as explaining the origin of the discrete symmetries of standard models that we normally see in our low energy theory, but we have no explanation for. There are other challenges, but my focus in this talk is to explain the origin of the discrete symmetries. And the key idea is that we look for them in the compactification space in Calabi-Yau Okay. These are broad statements about string theory that most of you are familiar with, but we are in the domain of heterotic strings, and there are two important gauge groups here. Well, only two anonymity free gauge groups, SO32 and E8 cross E8. And E8 cross E8 has turned out to be one of the more exciting approach to string model building, particularly because the matter spectrum arises on the 16 of SO10, which is a very interesting gut group. Mainly after the discovery that neutrinos have masses. Xenia spoke a lot about these geometries, but the key point of this slide is that if you assume a factorized geometry for your entire spacetime, and M4 plus X6, and you also demand that n equals to 1 supersymmetry be preserved in 4 dimensions, then X6 has to be a Calabi-Yau 3. There are limitations to such compactifications, and I won't get into it, but there are other approaches over non-Kähler, non-Calabi-Yau generalized geometries that we're going to have a look at. Now, broadly speaking, the string model building happens in 2 steps. The gauge group of string theory, E8, is essentially broken to the standard model gauge group in 2 steps. First, you take a manifold X and you define a vector bundle V over it, and GF you assume to be the isometry of X. It can be a trivial group as well, or it may not be trivial. Now, once you define the structure group of the vector bundle, we call it G, then the E8 breaks into this gut group across the structure group, which then eventually breaks into the standard model gauge group. There are various gut groups, E6, SU5, and SO10. They all are interesting. And they are based on different kinds of structure groups that you assume or construct for the vector bundles. Now, the second stage, where the gut group breaks to the standard model gauge group, is contingent, is dependent on the manifold X having a non-trivial fundamental group, i.e. not being simply connected. So therefore, once you construct a gut theory over the manifold X, the gut theory over the manifold X modified by GF has to be modified as well. My interest is when one does find the low energy theory, what kind of discrete symmetries actually survive this 2-stage process. Okay. Now, the problem is most known Calabi-Yau 3-folds are simply connected, and this is the Hodge plot that Xenia introduced. The y-axis is the height, the sum of the 2 Hodge numbers, and the x-axis is half of the Euler number. Now, most of these guys are simply connected, so which really impressed of Sheldon Cooper because he said you can't keep postulating multi-dimensional entities and not get anything in return. He has needs too. Fortunately, there was a classification of all the freely acting symmetries of Calabi-Yau three-folds, of a class of Calabi-Yau three-folds called complete intersection Calabi-Yau manifolds by Philip Rees Davis, Volker Brock, and making Sheldon Cooper, Dr. Sheldon Cooper very happy. Right. Now, I'm showing you again the tip of the hodgepodge now, which recently has been populating very fast. And some of these points were added by us in this publication. And this is the Calabi-Yau threefold with hodge numbers 1, 1, which is the Calabi-Yau with the least height. Anyway, so my question that I'm trying to answer is, what are the symmetries of the quotient manifolds? So you take a Calabi-Yau X, and you, from this classification that I showed in the previous page, you have the freely acting group. So now my question is, what are the symmetries that are still left over that have not been quotiented out and can possibly survive as symmetry of the low energy theory? So mathematically stated, this is the statement of the problem. So you have a Calabi-Yau manifold embedded in an ambient space because we're looking at the class of complete intersection Calabi-Yau manifolds. This A is a product of complex projective spaces, and GF is a finite group. And we want to know its group of linear automorphisms of this manifold. And the fun thing about this class of manifolds is that there are several of them. There are around close to 1700 such pairs of Calabi-Yaus and freely acting symmetries. And without telling you how I did it, I'll just tell you what I got. Okay, no time for this. These are examples of Calabi-Yau, complete intersection Calabi-Yau manifolds, represented as matrices of degrees of polynomials. No time to get into the details, but I'll give you some examples of the symmetries that we have found. So this is the Schwann manifold, and it's a 3-generation manifold. A lot of Euclid models have been constructed over them, and what we found from our classification is that this guy has a leftover Z3 squared symmetry product Z2 symmetry group on one of its Z3 cross Z3 quotients.
I'm afraid I have to interrupt there. That's what's up there. Are there any questions?
Would you care to elaborate on this last slide?
You shall receive your payment. Yes. So what we did was we took the entire class of complete intersection Calabi-Yau manifolds, and since all their freely acting symmetries were known, this is a summary of what we found. So we found that on all these Calabi-Yau quotients, there are still a lot of remaining symmetries which can potentially survive as symmetries of the low energy theory. So all these different groups that you see on the first row are the leftover symmetries, and the ones in red are actually our symmetries, which we checked by looking at the action of the symmetries on the homomorphic threefold. And our symmetries are particularly important because sometimes they help protect the proton from decaying in supersymmetric channels. So interestingly, we found that there were a total of 1695 CC quotients, Calabi-Yau quotients, and almost a fifth of them, probably more, ended up having leftover symmetries, and some of them are pretty large. And I'll also show you this other one. The last page was actually showing you symmetries where the action on the complex structure moduli space was trivial. Whereas here, we sort of looked at much broader terms. We looked at cases where the complex structure moduli space points can move while still remaining in the same class of Calabi-Yaus, and these symmetries are much larger. This is a work in progress, really. So, yeah.
It's like Challenger.